Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the Content Delivery Network, the distributed system that serves web pages, images, videos, and APIs to users around the world with low latency and high availability. We'll cover how platforms like Netflix, YouTube, Cloudflare, Akamai, and Amazon CloudFront use edge caching, GeoDNS, origin shields, and purge strategies to deliver content at global scale. Whether you're preparing for a senior engineering interview or building global infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the Content Delivery Network, the distributed system that powers fast, reliable, and scalable delivery of web pages, images, videos, APIs, and software updates to users around the world. If you have ever wondered how platforms like Netflix, YouTube, Spotify, Akamai, Cloudflare, or Amazon CloudFront serve high-resolution content to millions of users with minimal buffering, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core mechanisms, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building global infrastructure, let's get into it. Here is the core problem. A media company launches a new video series and suddenly millions of users across Asia, Europe, and the Americas are trying to stream the same high bitrate files at the same time. Every request goes back to the origin data center, which is thousands of miles away from many users. Latency spikes, videos buffer, images load slowly, and the origin servers start to crumble under the load. During traffic surges, the origin may even go down. The business needs a content delivery network that caches popular content close to users at edge locations, routes each request to the nearest healthy point of presence, shields the origin from traffic spikes, and keeps content fresh when it changes. Without a CDN, global scale is simply impossible. Let's walk through the functional requirements. First, the CDN must cache static and semi-static content such as images, videos, JavaScript, CSS, fonts, and software packages at edge nodes distributed around the world. Second, it must route each user request to the optimal edge server using GeoDNS, Anycast routing, or latency-based routing, considering geography, server health, and current load. Third, it must support cache invalidation and purging so that updated content can be propagated quickly when an asset changes. Fourth, it must provide origin shield and tiered caching, where a parent cache layer reduces the number of hits on the origin data center. Fifth, it must support security and delivery features such as HTTPS termination, compression, rate limiting, DDoS protection, access logs, and real-time analytics. These 5 capabilities make a CDN a complete delivery platform, not just a cache. Now the non-functional requirements. The CDN must be extremely low latency, serving cached content from an edge location that is geographically close to the user. It must be highly available, with redundancy across many points of presence and automatic failover when a node fails. It must scale horizontally to handle traffic spikes, live events, and viral content without manual intervention. Cache consistency matters. Stale content hurts user experience, while excessive freshness checks waste origin capacity. The system must be cost-efficient, balancing edge storage, bandwidth, and origin egress costs. Security is critical because the CDN terminates TLS and sits in front of the origin, so DDoS protection, WAF rules, and bot mitigation are essential. And finally, observability matters because operators need to detect cache failures, origin health issues, and regional latency regressions in real time. Here is the high-level system architecture. On the far left, end users and client devices request content through browsers, mobile apps, or streaming players. The request first hits a DNS resolution layer, which uses GeoDNS or Anycast to return the IP address of the closest healthy edge point of presence. The edge POP receives the request and checks its local cache. If the object is present and valid, it is served directly. On a cache miss, the edge POP may fetch from a parent cache or an origin shield tier to avoid overloading the origin data center. If all cache layers miss, the request finally reaches the origin server, which could be a web server, object storage bucket, or media backend. A control plane manages cache configuration, purge requests, certificate provisioning, and analytics aggregation. A monitoring and analytics backend tracks metrics, logs, and alerts across the entire network. The key metrics to memorize: cold cache hit ratio, the percentage of requests served directly from the edge cache without touching the origin. Time to first byte, or TTFB, which measures how quickly the first byte of a response reaches the user. Origin offload, the percentage of total traffic that never reaches the origin, which directly reduces cost and load. Bandwidth and throughput, measured at the edge, origin, and inter-cache tiers. Error rate, including HTTP 5XX and 4XX responses at the edge and origin. Latency percentiles such as P50, P95, and P99, especially for cache hits versus cache misses. And cache freshness or stale content rate, which measures how often users receive content that is older than intended. These metrics are what the business actually cares about. Let's trace the end-to-end user journey. A user in Mumbai opens a streaming app and clicks a trending trailer. The app requests the video manifest from the CDN domain. GeoDNS resolves the request to a point of presence in Mumbai. The edge server checks its cache and finds the first video segment already stored locally. It streams the segment to the user within milliseconds. As the user continues watching, subsequent segments are served from the same edge. When the content creator uploads a new version of the trailer, the media platform sends a purge request to the CDN. The edge cache invalidates the old asset and fetches the new version on the next request. The user refreshes the app and immediately sees the updated trailer. The entire journey happens without the origin data center being involved in every request. The core mechanisms and algorithms. The caching policy decides what to store, how long to keep it, and what to evict when storage is full. Common eviction algorithms include LRU, LFU, and size-weighted policies. The cache hierarchy uses multiple tiers. L1 edge caches close to users, L2 parent caches that aggregate missed traffic, and the origin shield that protects backend systems. Cache invalidation and purge allow operators to remove stale content globally or per region, implemented through APIs, tags, or time-to-live expiration. Request routing selects the best edge server based on geography, latency, capacity, and health. Origin shield and request collapsing collapse concurrent identical misses into a single origin fetch. Health checks monitor edge nodes and origins, and failover reroutes traffic automatically. The key trade-off is cache hit ratio versus freshness. Longer TTL improves hits but risks stale content, while aggressive purging improves freshness but increases origin load. Now the low-level design deep dive. A request arrives at the edge pop and is normalized into a cache key based on the URL, query parameters, headers, and accepted encodings. The edge cache looks up the key in a high-performance key value store, such as an in-memory LRU cache backed by SSD. On a cache hit, the edge checks the TTL and freshness rules, then streams the response to the user. On a cache miss, it consults a parent cache or the origin shield. If the parent also misses, the origin shield fetches the object from the origin. The response is stored at each cache tier on the way back. A purge service accepts invalidation requests, scans the cache key index, and removes matching entries across the edge and parent tiers. The cache key table stores the object metadata, TTL, tag, last modified time, size, and compression variant. The analytics pipeline logs every request and feeds dashboards and billing systems. For large objects, range requests and partial caching are supported, so that a video can be served in chunks. Key takeaways for your interview. First, a CDN is fundamentally a distributed caching and reverse proxy network, so emphasize cache hierarchy, request routing, and origin shielding. Second, always distinguish between cache hits and cache misses, and explain how tiered caches reduce origin load and cost. Third, cache key design and TTL policy are central to correctness and performance, so be ready to discuss query parameter normalization, vary headers, and stale while revalidate behavior. Fourth, the hardest design challenge is balancing cache hit ratio with content freshness. So mention purge strategies, TTL tuning, and conditional requests. Fifth, security at the edge is non-trivial because the CDN terminates TLS and fronts the origin, so discuss DDoS protection, WAF rules, bot mitigation, and access control. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the Content Delivery Network. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the Content Delivery Network. We covered the full picture, from edge caching and GeoDNS routing, through cache hierarchy, purge strategies, origin shielding, and the low-level design of cache keys and request flow. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.